Yeah. So, hello everyone, and thank you for attending this session again. We will be talking about formal explanations of machine learning based decision making processes and fairness. And our host today is Belona. Belona is a PhD candidate in the Research School of Computing at the Australian National University. Her research focuses on formal explanation and fairness in AI systems, with a strong preference for health applications. Prior to the Australian National University, she earned a master's degree in artificial intelligence from the African Institute of Mathematical Sciences in Kigali, Rwanda, and a bachelor's degree in computer science from the University of Ngaoundere in Cameroon. Belona is also the founder and promoter of BEL'S AI Initiative, a legally registered association in Cameroon that promotes AI for good through sensitization and education activities. So, Belona, thank you for being with us today. You have the floor now.
Thank you. Hello, everyone. Wherever you are, it's a pleasure for me to be there. And today we will discuss fairness through the lens of explainability. So I hope you are seeing my slide. If not, just let me know.
Yes, perfect.
Okay, so I will basically talk about explainability in general, but I will focus on formal explanation, which is what I'm using right now in my current work. And you already know me. I'm Belona Sona, PhD candidate, and this is the outline of my presentation. I will first of all explain a little bit the the need of explain machine learning models, and then we talk about formal explanation and follow with fairness, the connection between fairness and formal explanation. And the last part, we will discuss how we can assess unfairness or fairness in decision making process using explanation. Um, so, why do we need to explain model? Basically, one drawback of not explaining model is that one drawback of adoption of machine learning model or AI model right now still um, the nature of machine learning model, the way they are conceived, they are still black box model, and people are are in need to understand how the decision process behind AI model works. For that reason, this is the first reason that people want the model to be explained to understand how the decisions are made. Secondly, explainability is one of the pillar of AI ethics and principle among others. Explainability builds that trustworthy relationship between AI model and the end user. And it's also important to explain model for the for four main reason. The first one, as I already said, is to ensuring transparency. The second one is to also to check by the explanation if the decision making process behind is fair or simply is not biased. And also explaining a model help us to uh, ensuring a good interaction with the end user. This is just to say that if as an end user you are able to understand how things work in the model, you are more confident while using the application. And finally, explanation also help us to ensure improvement in the sense that if I know the reason why I'm accepted, rejected, or having a particular decision from a decision making process, it can help me improve myself in the case that, for example, I'm not admitted in the university. If I know the reason why I wasn't admitted, it can help me to improve myself in order to have better result in the future. Okay, to explain model, there are basically two type of approach. There are non-formal approaches that can be that can be categorized into type, local and global. But also there are another approach that are called formal methods, um, that help. Those methods actually help to justify the decision made by the decision making process. We will talk about later. We go deep about each of the type later in the presentation. As I was saying, non-formal explanation can be categorized in global approaches and local approaches. In general, in global approaches, the aim here is to find a simple model that help us to understand that help us understand how a more complex model works. As you can see here, um, we have a model which is very hard to understand, and then we will find a kind of simple model that will help us to mimic the original machine learning model, and will help us to understand uh, the machine learning or the decision making process behind. We also have local approaches. Local approaches basically help us to understand, like, we use help us to what is going on in local approaches is that we don't necessarily understand the entire decision making process, but what we do is that at each stage or at each point, at each locality on our decision making process, we are looking for a good explanation for this, for a particular point. This is how local approaches works. And then, sorry, and then we have formal explanation, which is um the type I'm working on, which can also be categorized into type. We have abductive explanation. What does it mean? In adaptive explanation, we are trying to answer the question why. Example, is my why am I accepted by the system, or why am I rejected by the system? The answer of an example of answer will be, you are you are accepted because you do have a good GPA and pass the entrance exam. So this is the kind, in when we are interested in adaptive explanation, this is the kind of the kind of explanation we want to give to the end user. And also we have contrastive explanation. In some situation, people will call it counterfactual explanation. And here, what we are trying to answer is the why not question. For example, why is my admission application not accepted by the university? The answer here will be something like, you will get an admission after you get some work experience. So here, contrastive explanation help us for improvement. What we were highlighting before. Contrastive explanation give us the change we need to make in ourselves in order to have better result, or the result expected. Sorry. So what we can keep in mind so far in the presentation is that machine learning model or decision making process need explanation. We have formal and non-formal approach to explain machine learning model, but in this presentation we focus on formal methods, and then to answer the why and the why not on the specific decision. Formal explanation could also be benefit to assess fairness in machine learning make in the in AI model. And in the next slide, we will discuss the formal of the concept of formal explanation. So, what is formal explanation? Before we answer this question, I will first explain you the setting of the setting of formal explanation. Actually, formal explanation is kind of a post hoc explanation. What does it mean? When we are working with formal explanation, we work after the model is trained. As you can see here, um, we have a data set, we're training a model, and at the end of the process, we have a trained model. And formal explanation, what we are working is actually on this part when the model is already trained. And what we do to get formal explanation, first of all, we have to transform the trained model in SMT SMT formula. As you can see here, SMT formula is a kind of logic formula. If I hope you are familiarized with logic in mathematics, logic mathematic logic. So MCT model, in formal explanation, we first transform our trend model in a SMT model, which is kind of a logic formula. And then we ask we use query, which is made of individual and their final decision, to get the explanation of their decision. I hope later you will understand better what is a query. So basically, to make it in a simple word, we have our trained model. We transform our model into a logic formula, and then it's easy for us to ask question to the logic formula and get explanation from there. So this is where we are working on. That's why we call formal explanation it's a post hoc explanation, because it's made after the model is trained. Okay, to make it simple, we will have an example, a study case example that will help us to understand concepts in the presentation. So we will use an example of university admission system, where this is the feature that people the feature that the system is using. We will have the exam entrance, which is that will be one if the applicant pass it, or zero if not. We also use this feature called first time applicant, and we also look at the work experience, the GPA, if the student has a car, if the student requested a scholarship, if he's coming from a rich hometown, if he has a good recommendation letter, a strong recommendation letter or not, if he's an overseas student, and if he already have some scientific publication. So this is the feature our system will use to make the final decision. So, what informal explanation, what will be the problem to solve? Let's take the case of this student called Amina having this specific feature. One here means that if I come back, if means that she has passed the entrance exam, and zero here means that she's not a first time applicant, and so on. So this is just an example of individual that will be used so in the next slide, what we do is to compute explanation from this individual. So Amina is accepted by the system, and we want to understand the reason why. So, as I told you in the beginning, before informal explanation, we have abductive explanation and contrastive explanation. So here we want to know why Amina is accepted. So what we are looking for is some abductive explanation. How to do that? First of all, this is, I mean, don't take it so, I mean, this is just to formalize what we are doing. So in general, we will use X like a space of individuals submitted to our application or to our system, and then big X will be this domain space, and small x will be an individual. So in our case, Amina can be just can be like Amina is an example of small x. We have the domain space of the decision. In our case, it is a binary space, which is 0 or 1 0, whether you are not accepted, and 1 if you are accepted. And we have delta here will be considered as the trained machine learning model. And we have XP, which will be a property of an individual. So um, being a property of an individual means that XP is a subvector of X. We say that X is an individual. XP is a subvector of X means that it's a characteristic. It can be, if I stay in our example, XP can be something like have pass and like pass being a first time applicant and requesting a scholarship. This can be considered an example of XP. So now that we know all the notation, we can define an explanation or an formal explanation for an individual as a set of feature that the individual needs, or the set of future that that is responsible to trigger the final decision of that individual. In simple word, an explanation will be this subvector that that is necessary to the machine learning model to make the final decision concerning that person. I hope it's clear. For now, if it's not clear, you can just stop me and ask your question, because it's really important to have this definition. A formal explanation will be a subvector that is responsible to trigger the final decision of an individual. By consequence, all people sharing that property are supposed to have the same final decision. Example, in our case, if we consider that having a good recommendation letter and being an overseas student is an explanation, it means that everybody having a good recommendation letter and being a strong and being an overseas student should be accepted by the system. Okay. In our case, we train a model on a synthetic data, and we end up like with this kind of explanation. So, for example, for this system, if you pass an entrance, if you pass the test, the entrance exam, you have a good GPA, and you are an overseas student, it's not an explanation. But if you have a car, you are not requesting a scholarship, you have a good recommendation letter, uh, and you have a good recommendation letter, this is an explanation. If you have a work experience, you have a good recommendation letter, and you request a scholarship, you are this is an explanation. So this is the kind of explanation, this is the example of for explanation, how the formal explanation are set, how they how how they look like. When we compute an formal explanation, this is how it will look like. That will be a conjunction of your feature, for example. Okay, to make it simple, this is an example. If you remember our individual Amina with this feature, this is kind of the state how we do to compute those explanation. Basically, what you do is that as first you consider that Amina itself with all the feature is an explanation. And what you do is that we just look for the small subvector of Amina which is necessary to take the final decision. In to make it, I mean, for this result, what you will do is that you will subsequently remove constraint on the feature and see whether um the rest of the vector still acceptable by the system. As you can see here, we will start first with the first feature is the entrance exam. When you see this symbol, it means that we no longer have constraint of this value. In Amina, the value is 1. But when you see this symbol, it means that we have removed the constraint. In simple word, it means that do we need is Amina need this feature to be accepted by the system. This is actually what it means in simple word. This first line means that do the do Amina needs to have passed the entrance exam to be accepted by the system. And what you see here is the answer of the logic model. He will tell you no, this is the symbol, or no, or yes. And this is the symbol of yes. So as you can see here, we will subsequently ask it to the model. First of all, at the first line, we ask, do Amina need this feature to be accepted by the system? The system tell us no. And when the system tell us no, we keep this, we don't change, we continue with the second one. As you can see here, the second line we just mean, do Amina need to pass the entrance exam and be first time applicant to pass to be accepted by the system? The model will tell us no. We will continue until this line. From the line number 5, the question will be, do Amina need entrance exam, first time applicant, work experience, good GPA, having card to be accepted by the system? Here the system say yes. When the system say yes like that, what does it mean? It means that the new feature we were looking at was necessary for the decision of Amina. In the Because of this yes answer, you will see that in the next line we will we will put again the constraint on this value. It means that the this future car is necessary, so we will put his original value, and we will continue. So each time the model say yes, it means that the future we were looking at that moment is necessary. That is how, at the end of the day, to have to see what is an explanation, we just have to look at where in the last line where you have the original value of the future. As you can see here, the system need the future C, need um need the feature S, need the feature R, and the feature L to make the final decision. So we will say that an explanation will be a conjunction of C, of S, of R, and L. Okay, as you can see here, what does it mean is that uh, Amina was accepted because she has a car, because she has not requested for a scholarship, because she's from a rich hometown, and because she has a good recommendation later. But what you should know that is that um, for one individual, we not only have one explanation, we can have many explanation. And how to compute the other explanation? When you already have one explanation, you will repeat um the computation of the second one, and just make sure that he's not computing the one you computed before. And to do it, you will just put your first the explanation you already computed in the set of constraint that um your model should satisfy. I hope it's clear. So for Amina, for example, we have this first explanation that we already compute, but you can still have this one, and this one. So in formal explanation, what you should keep in your mind for now is that we are looking for a small subset of future that are necessary to take your decision. The second thing that you should keep in mind is that you don't only have one explanation, you can have many explanations. And just because of the way the explanation are computed, you should also understand that the space of explanation in formal explanation is monotone. Means that uh, okay, I think I won't go far deep in the space, but monotony is something that you can just mean that uh just help us to know that there is the notion of minimum explanation. When I say here is said the space should be monotone, you should just understand that we are looking for minimal explanation. Otherwise, we can have very long explanation and get confused. And so in the next slide section, we will discuss the notion of fairness in decision making process. If so far you have some question, you can just stop me and ask your question. It's fine.
Okay, so if you prefer we wait till the end, or you want like to take the questions right now?
What suit you best is okay for me.
Okay, so I think we can wait till the end if it's okay to
Okay.
everyone.
Okay. So in this section, we now talk about fairness and formal explanation. But before, what is fairness? What is fairness? Means everything and nothing at the same time. There is not really a formal definition of what is fairness. Fairness is a contextual notion that people define in a particular setting, and that's why it's not really easy to find a global definition of fairness. But however, we know that the concept of fairness become interesting when we don't want to discriminate a particular group or a particular people. The fairness is there to make sure that the system doesn't discriminate anyone. And in most of the time, fairness also matters when in our data set or in our individual, there are some variables or feature called protected variable that we don't want to use to make our final decision. Okay, this is in this slide, what I'm presenting to you is some views of fairness. In fairness, people can look at fairness as equal odds. Means that in equal odds, what we tend to do is that we don't want people who are similar to have different outcome. You can also look at it at predictive parity. Means that if we have if for example, if we are belonging in different subgroup, and we have, let's say that in predictive parity, it means that if we are dealing with people with different subgroup in our data set, we just want to make sure that the change of each subgroup is the same. And we have counterfactual fairness. Counterfactual fairness just tend to say that if you just want to make sure that if people differ only on the protected variable, um, that decision are not made on the protected variable. Let me make it simple. Let's say in the case of our admission system, if Belona and is the only difference between Belona and someone else is just on the gender, they should have the same outcome. If they don't have the same outcome, it means that the gender was crucial to make um, the final decision. And in that case, the system will not be fair if we have different outcome, and will be fair if we have the same outcome. In our work so far, in our the next of present in the next slide of the next slide of this presentation, we will look at the fairness in the counterfactual way, because it's make it easy with the formal explanation. Okay, first of all, what is a protected variable? As I just say before, protected variable is a variable that should not influence the decision making process. In general, when we talk about protected variable, people will just think about demographic in general variable, but in some situation, the protected variable is something different. It can be it's something different. You just have to look at your data set, or ask for people. For example, if you are working in healthcare, you can have some sensitive variable. For example, in our the current example I we are using in this presentation, the protected variable should can be which hometown. For example, we don't want we don't want the decision to accept or reject people based on whether they are coming from a rich or a poor hometown, for example. So in this case, for example, our protected variable is not a demographic, but since something that make difference, social difference between people. Okay, so this is the notation we will use. So P is the protected variable, big P is the set of protected variable, and this notation X of XP means that people who are, let's take the case of Amina. Do you remember that small x is Amina? This XXP just means that people who defer to Amina only on the protected variable. It's really important for for our presentation. Yeah, so you should have this notation in mind. X of P means that people who are similar like me and only differ with me on the protected variable. And in that context, what will be an unfair decision? An unfair decision will be we will say that a decision is unfair if people who differ with me only on the protected variable have different outcome, have different outcome. Like Belona, I'm accepted by the system, but there is a male which is who has the same characteristic like me, like he also passed the interest exam, he has a good recommendation letter, but just because he is a male, he's not accepted by the system. In that case, we say that the decision making process is not fair. Now, if you remember, I told you that when we compute explanation for an individual, it's not a single, it's not is not always for a particular individual. We can have many explanation. So we consider that the machine learning model or the decision making process is unfair to an individual is if all his explanation are unfair, means that all his explanation has the presence of a protected variable. So this is just the consequence of this definition or of this theorem. Okay, so far, what you can keep in mind is that the notion of fairness occur when there is a high risk of discrimination of people, of subgroup of people in the data set. Secondly, we should keep in mind that a decision is unfair if individuals that differ only on the protected variable have different outcome. And now in the next section, we will discuss how we can use formal explanation to assess fairness or unfairness in machine learning model, which is actually the clue of this presentation. So first of all, we know that explanation inform about the future that are relevant for a decision. And then we also know that decision making process is fair if it does not rely on protected variable. So this is clear. Okay. Now, what is an unfair explanation? What can I say when I see an explanation? How can I say where or when can I qualify an explanation as unfair? As an explanation is considered as unfair if it contains a protected variable. Let's say in my explanation, you see something like you are accepted because you are a female. Just because I see you're accepted because you are a female means that this explanation is unfair because female gender is a protected variable. So from this definition, we have two theorems that we appear. First of all, we will say that decision is unfair with respect to the individual X if all the explanation that justify the decision of X are unfair. This is if the consequence of this definition. If all my explanation has a protected variable, it simply means that the decision process is unfair is unfair with me. Also, the second theorem is that if someone have one of its explanation which is unfair, it means that in the system there are people who are suffering from discrimination. So this is a lot of proof behind, but you can just take it that way at that time. The most important theorem in this slide is this one, because this that help us to check whether the model is fair or unfair. I will explain again. If I compute explanation of an individual, and in the explanation I see that one of explanation has a protected variable, it means that the decision making process is unfair. And also, if I compute the explanation for a particular individual and all its explanation has a protected variable, it means that the system discriminate that person based on that protected variable. This is the main thing to keep in mind from this slide. And then what is the pro and cons of using protected variable to assess unfairness? The pro, the advantage is that we know how to compute explanation, and because we know how to compute explanation, you can we it's easy for us to check only on explanation. If the explanation exhibit the protected variable, it's easy for us to see that the model is fair or unfair. But the cons of this method of using protected variable to assess fairness is that um, in some time the protected variable can be absent in explanation, but then there could be some proxy variable that um, that still highlight the presence of the original protected variable. So if you just base your access fairness using protected variable, you can be misleading by the proxies of the protected variable. So this is the cons of using uh, protected variable to access unfairness. How to solve this problem? Uh, you should deal you should deal with proxy discrimination. Proxy discrimination is when the decision-making process is influenced by a variable or a combination of features that are reproducing the effect of protected variable. Example, if we stay in our example of university admission, we will see that our protected variable here is R, means that we don't want our decision process to rely on whether someone is coming to a rich hometown to take the final decision. But what you see is that if even if we don't have the appearance of R in our explanation, if someone has a car and is not requesting a scholarship, it could mean that he's coming for a rich hometown. Simple. If someone is has a car and is not requesting a scholarship to attend a university, it means that he is coming from a rich hometown. So if you just rely on this protected variable to check whether the explanation are fair or unfair, this can mislead you if you see only this combination. So if you have this combination, he will still exhibit the presence of the protected variable, which is at first sight absent in the explanation. Contribution of proxy discrimination. If you are able to handle proxy discrimination, to handle proxy discrimination, you are added a value of the or in the assessing of fairness, because you are going deeper than just looking at the protected variable, and this is good. And but what the drawback of using of the proxy discrimination is that it's also very hard to identify all the proxy variable. Some proxy variable are easy to capture as the one I just showed you previously. But in some case, you can have a combination of 2, 3, 5, 6, 10 variable that reproduce the effect of the protected variable. So it's not a straightforward path to identify all the proxy variable. That's why it makes the process a little bit difficult. And also how to deal with the problem. What we are trying to use in my work is the notion of background knowledge. What is background knowledge? Background knowledge is information that we have about the system, yes, the information that we have about the system that help us to capture what is realistic and what is not realistic. Okay. The benefit of using background knowledge is that, first of all, it will reduce the size of explanation, and also reduce the number of explanation. But later also, we see that background knowledge can also help us to assess unfairness, in the sense that, for example, let's see here. Okay, before um, background knowledge to be used to assess unfairness should be represent in form of if and then rules, like because when we are working on formal explanation, we are working with logic I mean, it looks like a logic formula. It's also necessary that our background knowledge is a condition, because the if then rules can easily be translated in a logic relationship between our future. Okay, now let's say that for this particular current example we are using, we have this background knowledge. If a student is coming from a rich home time, then he owns a car. If a student is having a good GPA, then he's having a good recommendation letter. If a student owns a car and not requesting a scholarship, he's coming from a rich hometown. So this is how background knowledge looks like. And how to get background knowledge. You can get background knowledge from the expert in the domain, or you can even have background knowledge from the people who ask you to build the model. Because if I request a decision making process to make admission in my university, I have some constraint that I want from the model, and this constraint will serve as background knowledge, and using them will help to, as you can see here, um, this is how you will transform this text, which is background knowledge, in terms of if then rules. As you can see here, this is how it looks like when we want to use them. We first transform them into if then rules or logic formula, and then we apply them. The importance of using background knowledge is that it can help us to identify the proxy of the protected variable, and also to it can help us to eliminate a combination that are not realistic. For example, if you see here, um, if you see here, yes, if you see, for example, yeah, if you see, for example, here the background knowledge number two, say if you have a good GPA, you will probably definitely have a good recommendation later. It means that if you see some explanation where G equal to 1 and we have a recommendation later equal to 0, this explanation is not realistic because of the knowledge you get from the background knowledge. That will help you to see that no, this explanation is not realistic, so I don't have to check it or access it. And this is good because sometimes some explanation that we consider as unfair are actually not realistic. So instead of qualifying a decision as unfair because of this explanation, we will just eliminate this explanation because in real world it could never happen. And this information we get it from the background knowledge. Okay, how to use background knowledge to assess fairness. First of all, as you can see, how you should state the logic relationship between the protected variable with one of many variable, and also you should state a logic relationship between the final outcome with one or many variable. Of course, because if you want to use background knowledge to assess fairness, there should be a relationship between your protected variable and some variable in your background knowledge. Otherwise, that will not be helpful. And this is the big work that we have to do. But as soon as you have this is helpful to incorporate it in your computation of your explanation, but also to assess unfairness. So finally, what we can keep in mind there here is that assessing unfairness in decision making process explanation require more than just identifying the protected variable. Secondly, assessing process discrimination is a better way to assess unfairness in decision-making process through explanation. And at the last point is that background knowledge is a good way to make the identification or the use of proxy discrimination more efficient and more realistic. And to take back home is that explanation is really needed right now to make sure that the end user to build a trustworthy relationship between the machine learning models and the end user. Secondly, fairness matters a lot in decision making process because um, uh, it's completely not realistic to have a data set where people are represented in the same way. Just because of that, the risk of a discrimination in machine learning model, it's very high. So fairness is really necessary, is really helpful or necessary to take into account to make sure we did not harm or discriminate people or a group of people. Now, third, explanation can help to assess fairness because formal explanation actually rely on feature and show us what the model is looking at to make the final decision. In that case, if computing our the formal explanation show us that the model is not looking at the right feature to make a decision, we can use them to assess whether the model is fair or unfair. And finally, background knowledge could be helpful to assess unfairness through explanation. This is let's say a good trade-off between uh, just identifying the protected variable and actually eliminate any source of discrimination through the protected variable and its proxy in the decision making process. And this is what I have for you for today. Thank you for being there, and I'm okay to answer your question. Thank you.
Thank you very much. Thank you very much. We have three questions, I think, in the chat. Okay.
Okay.
So the first one is what will be the main difficulties if you consider non-Boolean variables in the explanation process?
Come again, please.
So what will be the main difficulties if you consider non-Boolean variables in the explanation? And like,
Non-binary.
yeah, non-Boolean.
No,
Like,
non-boolean. Yeah, okay, it's same thing. Okay.
so like I
um
mean, and he explained, I mean when you consider that variables can take one, two, and three states, for example.
Yes, this is a very good question. I took this example with Boolean to make it simple, but actually, when you are not working with Boolean and you are working with other type, you will still have the value of the value of your variable will still be a constraint, but as a result, you won't have a simple like one answer. The explanation should be will be something like anytime someone have let's take an example in healthcare. Anytime the number of cell blood of someone is between, let's say, 100 and 200, he will be sick. So when you are not using boolean, you will definitely have a subset of number in your explanation. So instead of having one point, you have a subset.
Okay, so if I understand well, we can just transform anything into a boolean because like it's just, let's say you're saying if x belongs to 100 and like is between 100 and 200, so that's like basically a boolean because you're asking if it belongs there, then it will be one, otherwise it will be zero. And I think you can transform pretty much anything into like a series of booleans, right?
Exactly, this is the logic behind actually. Yeah.
Okay. So the other question from the chat is the protected variable always unique? And I think, yeah, we have, yeah, I'll let you answer.
No, no, it's not unique. That's why in the concept you will see that I have small p, which is a protected variable, and then I have big P, which is the set of protected variable.
Yeah.
You can have one, you can have many, and you can even have a combination of feature who are that are the protected variable. So it's not a single feature. It can also be two feature that serve as protected variable.
Yeah, and the third question, still from Usman, do you think that this methodology can be used for GNN architecture?
I am not sure about that because I didn't look at. But what I can tell you is that if your question is, can we use this method for non-structured data such as image and image? Yes, we can use it on images. Is what I'm right now I'm using as my in my like image data set. But GNN, I'm not sure. I didn't look at. I didn't check it, so I can say.
Okay, so yeah, I think graph neural networks. I'm not sure, and yeah, I'm really interested to know like I have a few questions and related to image or any other type of input. So, like, how do you transform the model, like the process of transforming the model into an SMT model that you can query? Like, how does it go? Let's say for an image, how are we doing that?
Basically, this is that will be a simple way. You will have to just flatten your image first. To flatten it as a long vector first. But this is not your problem because at the end of the day, if for example, let's say you are doing a segmentation that you want to highlight an area in your image, the area of interest, if we just capture the feature, the pixel that are part of this section, and at the end of the day you can just project your answer on the original image and capture the region of interest on in your original image. And that would be an explanation like, if someone is sick, it's because this, we just highlight the region of your image that is responsible of the sickness of the person. You understand what I mean?
Yeah, I think you like when you're talking, I'm thinking about saliency maps. Is it
Probably.
okay? Because
Mm,
yeah, so let's say like the thing is I have an image to classify. I put the image into the model, and like I want an explanation, and then it gives me back the region it thinks that had the more influence in the decision.
exactly.
Okay, because like those models, I don't know, saliency maps sometimes they are not that reliable, and it's like really tricky. So yeah,
Mm.
so
So
okay.
this is exactly the idea behind. So you will first flatten your image, like just you will see your image like a set of points, just as a set of point. You will compute everything as normal. At the end of the day, we just project the the pixel or the point that are necessary to make the final decision, and you will see that the point those points we capture in your image, the region that are responsible to the final outcome.
Okay, because my first intuition was that you pass the image through the neuron, and at some point you just catch the activations of the, I don't know, the final layer, something like that, before before the final layer, like the penultimate layer.
Mm,
And then you use that representation to do things. But yeah, it like yeah, you know better, and it perfectly makes sense to use the pixels directly, even though like flattening images, I don't know, I find it very un like counterintuitive, unintuitive. Yeah.
mm.
Yeah. So that was one of my questions. The other one was like, when you say we ask the system about like, is this feature necessary for the for the decision, what are we doing? Because we are talking here about binary like binary boolean things. Are we just switching them, like just
We are not. This is I Are you familiar with constraint programming?
yes?
So, in constant programming, you consider the value you have for a particular feature as a constraint. let's say my name is Belona. Belona is a constraint to have the NG. I am Belona, but I'm also a PhD candidate. I'm also, all those values are considered as a constraint that makes my individual.
Okay.
So now what you are doing is that you remove the constraint on the name. Like, if the name is not Belona, if the name is whatever, that's why you will see the semicolon. Like, Belona is no longer a constraint.
Yeah.
Do we still have um a positive answer? Means that it can be someone else, any name. Should we still have, you see now, you understand? So you just remove the constraint. It's
Yeah.
not like you flip the value, you remove the constraint on the feature.
Okay. Like, yeah.
Yeah.
No, no, I have an idea. When you talk about
Mm.
like constraint programming and removing constraint, then it makes perfect sense. And yeah, I had another question, but I think it was answered through like implicitly through the presentation. But I will still ask it. Maybe it can help someone else. So, what would you say to someone who said, yeah, like if we don't want the model to use some protected variable, let's just delete it and hide it from the model.
It's a very bad, it's a very bad idea. This is something that this is the first thing people were doing to say, okay, now I train my model without the protected variable, so I'm sure that the model is fair. But actually it's not fair. First of all, because some proxies can still highlight the presence of the protected variable, but also in some situation you cannot just remove the protected variable. Let's say in healthcare, for example. In healthcare, the gender is important to choose the treatment, to choose the medication, to choose everything. In some situation, you can't just remove the protected variable. You should deal with the protected variable. So removing the protected variable is not the solution. And even that, if you remove the protected variable, there is no guarantee that you still not have the influence of the protected variable by the other data set. Because at the end of the day, let's if you see the process that may people use to actually select the future for a decision making process, at some point all the features are related, because it's not the feature are not selected. Like, let's say let's say for example, I want to for the let's even take the example you are using for university admission. The the effect of this each variable is not independent. They are not completely independent, and just because of that, there is no guarantee that the removing one feature, uh if you remove one feature, the influence one will not disappear at the same time, because they are not independent. The probability that some other features still replicate the effect of this variable is very high.
Yeah, yeah,
Yeah, yeah.
totally perfect, and like makes perfect sense. And like I think I have been like in a presentation where it was about medical imaging, and there was a fun fact, which was that on radiographies, people were able to like neural networks were able to say this is radiology from black people and this is a radiology from not black people, like from white people. And
Yes.
it was funny because a human could not make the difference, but the machine.
Mhm.
And yeah, I found that funny that those kind of tricky things that we won't even think about, machines can pick up on them and maybe use them to make decisions.
Yes, this is because, as I was telling you, whatever we say, when you people think about some future to make a decision, in general, the future are not independent. That's why. So they are somehow related.
Yeah,
And as in our human scales, it's, let's say, easy for us to see the proxy when it's just a combination of two variables. But with machine, they are able to I mean, to see the proxy, which can be the combination of even 1 million variable, it can still reproduce the effect of the proxies.
Yeah, totally understand. So if there are no more questions, yeah, I think we are at the end of the session. So thank you very much, Belona. Thank you to others who attended this session. And yeah, it was our pleasure to have you, and hopefully we'll have you again.
Thank you so much. Bye bye.
Bye.